Hi, how's everybody doing today? Seeing some want to go to bed, go back to bed. So second exam's over. Again, if you didn't perform as well as you would have liked, you have the opportunity to retake that exam on the finals to do a replacement option for the exam. So the material as we keep moving forward is going to keep building. So if you don't feel like you've mastered a concept, the videos are there for you to go back and review and learn the concept. And then what is most important is practice, practice, practice until you feel like you have mastered that concept. So I can only explain so much. You have to do the practicing. So we're going to move into the next concept, which is op amps. So to be clear, this is me teaching you the concept of op amps. So this is a concept teaching. So op amps. So to start, I'm going to go with some background first. So when you look at some applications, there are, for example, communication between an implanted pacemaker and external device. So when you think about an application such as this device has to gather some information and then actually communicate it and send it through the body, because it's implanted in your heart. It has to come through your body, and then it's going to be received on the outside of your body. Do you think that this is going to be a very large voltage that can be sent through your body? It's going to be something really small, because otherwise it's going to hurt you. And so signals that are transmitted through the body have to be very small signals. So once they actually are received on an external device, they have to do what is called an amplification of that signal, so that you make something that was really small, make it really large, so that you can then understand and interpret that information. So that is one application of what an op amp does, is amplify a signal. Another one is thinking about like your cell phone or any other communications. As you send a signal, you want it to be something that's like a low signal, so it's not going to harm or take up a lot of bandwidth and create a lot of power and energy, and therefore create other things. So when signals are sent, again, they're kind of packaged up into this smaller signal, and then they're sent, and then it's received, and then you need to amplify that up again so that it comes out as a signal that you can make more sense of. So does that make sense of some of the applications? These are just a couple applications, but they're used throughout electrical and computer engineering applications. So I just wanted to bring some that you guys might kind of find cool. This is an example of one typical low-cost op amp. You can see all these components in there. These are called stages. So you have what's called a differential amplifier first, a high gain amplifier, and then a low output impedance amplifier. And what these do is they take in the signal, they increase the gain portion of it. So if your input signal is 1 microvolt, they may increase it to something that's more understandable in the volt range. Or it could be picovolts, and it wants to amplify it up to point volts of 100 millivolts, which makes more sense to all of us. So that's what these sections do. The first part of it is going to buffer the signal so it doesn't lose information. Then it's going to make it large. And then it's also going to have this stage that then whenever you put on a load, it doesn't change that again and reduce the signal again as it is connected to other things. So that's what these 3 stages basically do. So in here, we're not going to learn about what these are called, are transistors. In 2280, you learn actually how to make a single input. This has 2 inputs, but the one you'll do in 2280, you actually build these from these components. There's a BJT transistor and there's a MOSFET transistor. So you'll learn actually how to make an amplifier in 2280, which is your next stage, usually after this class. So in here, we're going to just look at an already built op amp. And so we need to understand what that is. So the symbol looks like this in a schematic, and it's going to be this chip. And on this chip is, it has 2 inputs. You have a positive input and a negative input. So two inputs. You have to give it power, and so it has its supply powers. So a plus power supply and a negative power supply. And then you have an output, and it's one output. So this is the symbol you're going to see. So you need to get comfortable seeing this symbol and understanding that you have two inputs to it, a plus side and a minus side, and then one output, and that in order for this to work, it also has to have power to it. So we're going to supply it with a power supply positive and a power supply negative. Sometimes the negative may just be ground, and then you might use like a 9-volt battery, or it could be ground and a 1.5 volt battery. So depending on what you're using, otherwise it might be a 1.5 positive 1.5 battery and a negative 1.5 battery. So overall you have 3 volts that is being supplied to this op amp. Op amps have different voltage ranges. There are low power ones that work on 0.8 volts, 1.5 volts. There are high power ones that need 40 volts. So there's a whole range depending on your application and types of signals that are coming in and out. All right, questions on what the symbol looks like. So you don't need to know internally what's going on. We're going to talk about externally. If this isn't a circuit, what do we do? And so the other thing about this is that you're going to build with these. So in the lab, you're going to have these chips. How you interpret the chip is that there's going to be this notch at the top of it, and this will be the top of the chip. So this is how you know the orientation of the chip. You then are going to look up a data sheet, and on a data sheet, it will show you an internal kind of connection like this. This one is an LM324, and it will show you the notch on it, and that again will be the top of your chip. From them, you also need to know what pins go to what and what number. So on here is the labeling on a data sheet. So you need to look up a data sheet, and it will show like this is where your 1 pin starts. It goes 1, 2, 3, 4, 5, 6, 7, and then it starts at 8 on the bottom and goes up to 14. So on this, each op amp, so this one is a quad, meaning it has 4 op amps on it. So if you only need 1 op amp, you need to find the connection for 2 inputs and 1 output to this. Then you need to also make sure you're supplying power. So that's the most common thing I see students will hook this up, and then they forget to put power. So make sure you troubleshoot by making sure is power connected. Otherwise, it won't work. So again, most common thing I see when students are like, oh, it's not working like I think it should. And I'm like, did you put power on it? So make sure you put the power supplies. And then you're going to identify where the 2 inputs, there's going to be a negative and a positive, and then an output. So in this one, your pin 2 would be your negative input, pin 3 is your positive input, and pin 4 is your output for that. So this is how you're going to build with it, is to put that into a breadboard, and then you're going to connect those wires to the correct components that you need. Okay? So now we need to move to another concept. So this concept is just understanding the schematic portion of the op amp. So all right, so now it's up to you guys to go and look at these in circuits and get comfortable seeing them and identifying them, understanding like, oh, this is a positive input, this is a negative, this is the output. If the power supplies are not drawn there, know that they have to be there. So that's the concept you need to take away from this. Yes?
So just to reiterate, in the inputs, we're sending like a low voltage into it and it scales that up to a higher voltage?
Yep, we're going to talk about that next. That's more of the characteristics of the op amp. So we'll talk about that next. So this first concept, though, If you know, it's up to you guys now to go practice this, look at circuits, understand that the two inputs, the output, and that there is power supplies to them. So that's the first concept. Okay, so now going to like, how do these kind of work? And so there are different ways that they work. So the first thing that we're going to understand is these op-amp rules. So these are the characteristics. So this is the concept of so I'm explaining the concept, and then it's up to you to go practice this concept. So the concept is that the characteristics of the op-amp. So the characteristics are that you have no current going into the plus or the minus terminals. So I'll label that plus and minus. So going in here, your I is 0. Okay, so that's one characteristic of this. Because of the power supplies on the output, the power supplies allow you to fix this output voltage based on your two inputs. So that's the second characteristic, is that your output acts like a voltage source. And is set by the input. The third characteristic is that the plus terminal and the minus terminal voltages are the same. So the voltage at the plus side is going to equal the voltage at the negative side. So these are the three characteristics that you have to understand. So it's easy for me to explain this. I'm explaining it. Now it's up to you to practice these and get comfortable with that concept. Okay, so we'll go over some examples, and then it's up to you to keep practicing that till you get it. Going back and rewatching this video is also recommended so that you hear it again, like, okay, and then writing it in your own words would be also another recommendation, is writing what these characteristics mean in your own words. All right, questions before I move on? Yes?
In the lab, we did like a comparator,
Uh-huh.
and the plus voltage and the minus voltage, you like compared them,
Mm-hmm.
and it like only had an output if like the plus voltage was higher.
Yeah.
But the third characteristic, you said they have to be equal. How does that work?
So it depends on how it's configured. So okay. So I will make a note. So you have different types of configurations. So this would be kind of the next concept that we need to talk about. Before we move on to that, any questions about the other basics? So current going into those are 0. Your output is going to be like it will act like a voltage source. So in that means that if I put a resistor here, a load resistor, that output does not change. It acts like a fixed voltage source that you've just put on a load resistor to. Yes.
This might be going a little bit ahead, but how will these be used in circuits?
Yeah, we'll get to there. That is a little bit more ahead.
And so the output voltage is determined by the power going into the
So it depends on the inputs coming in, and it gives you the supplies fix that voltage on the output.
okay.
Does that make more sense? Okay. Other questions? Okay. Also for this, if this doesn't make sense to you, read the book as far as the sections that are listed in the handouts and lectures, and also in the modules. So there's sections in the book to read. Asking other people to explain it to you in different words and different ways will also help you to understand and get more comfortable with this concept. So those are the things that I recommend that you do in addition to going back and watching this and going through the examples to assess, do I understand this concept or not? So the examples we go through in class are to assess, am I at the level of being comfortable with this concept? If not, that means you need more practice. And that's on you guys and that's an expectation that I have, that you go and do that on your own. There's lots of material out there to give you that practice. Okay, is that clear? Okay. All right, so as I said, like the model of this is gonna be that this output kind of looks like and acts like this voltage source, okay? So this is kind of what you can think of it as in there, is this voltage source on the output. So on here, this is called a comparator switch. So this is moving into another concept of configurations. So the concept of identifying configuration that you have to achieve an output value. So this is the first configuration, is called a comparator or switch. So with this, if you don't have any feedback, so maybe that's the other thing I could say here, is that for this concept, maybe feedback configurations. And this is used to solve those circuits to get an actual voltage output. If it's not in a feedback configuration, it will be a switch or comparator. And this operates by putting in a voltage at one terminal and comparing the two. The internal gain of this is very, very high. So if I have 3 volts on the positive side and 0 on the negative side, this is going to have that really large gain, and say it's 1 mega. So it's really large. So if I had that, what it's going to do is compare the two voltages, which would be in this case 3, multiply it by 1,000,000, and therefore you should have out of here 3 million. But that's going to be limited by what you supply it. So if it's a positive value, you're going to get out the rail of plus 10. And these typically are not ideal, so if you put in 10, you're going to have some voltage drop. Usually they're about 2 volts drop for most of the amplifiers you work with. So you're actually going to see out like 8 volts for 10 volts. Yes?
Why do we assume why do we assume?
You just know it's high.
Okay.
It will say specifically on a data sheet for a specific frequency range what that gain is, and it's usually high. So most of the time, we don't care what it is as long as it's high. Because as long as it's over, 3 times this to be over 10, it's going to clip it at 10 volts because you can't get more voltage than that in the circuit. So it just needs to be big enough that it's going to get over that.
So
Yes.
question on the MATLAB lab.
Yep.
It talks about how, our V out, it compares it and just says, okay, if our V in is greater, than, V in going into the positive terminal is greater than the V in going to the negative terminal, then our V out is just the, VDD, I think it calls it,
Uh-huh.
with a little bit of drop. Is there a difference between referring it to just that and this kind of formula we have right here?
No.
Okay.
So it's the same.
The same thing?
Yep.
Okay.
So here you see 3 minus 0. If we have, say instead, we have 3 volts here, so this is no longer ground, and we ground the other side, what would I get out?
Negative 10 volts.
You would have negative 10 volts out.
Give or take.
Yep. So whichever one has the higher voltage on it, it will give you that rail. And this is what a comparator switch does, is just compare the two and give you either a positive or a negative of those supplies minus a small drop.
Okay.
Yes, questions?
What is A?
A is gain.
Okay.
So that A naught is a representation, it's called the gain, internal gain. All right, other questions? Yes.
So this might be kind of ahead, but if you're trying to find like the internal gain, is it usually provided or do you have to kind of solve for that?
So it will be on a data sheet. And you need to learn what's called multiplots in 2280 to be able to read the data sheet to know what that value is. For us, we just need to know that it's large. So we're assuming it's large enough and that it's always going to act this way for a comparator. Okay? But as a designer and as you get more familiar with that, you're going to be concerned about what frequency range it actually needs to operate in. And those are the techniques you'll learn about in 2280.
So what you've done with the 1 million times 3 volts, that's just that equation down there.
Uh-huh.
And then so that's, we get V out equals plus 3 million, but because that's positive and only 10 volts are being put into it, it just stops at 10.
Correct.
As soon as 10.
Yep. Yep, so it can only go as far as what's supplied. So this might be a better way to word this. So for feedback configurations, the characteristic is that V plus is equal to V minus. And for switch comparator configurations, you're going to use this characteristic. So for comparator switch configurations. Okay. Any questions before I go on? Yes.
So you have plus 10 volts going into the top of the power and minus 10 going into the bottom, which means the potential difference across those two is actually 20 volts, not 10 volts.
Uh-huh.
So why is it that the output is 10 volts instead of 20 volts? It's kind of like in the MATLAB in the 1245 lab yesterday, we had the positive input was 5 volts and the negative one was ground. So the potential difference was 5 volts. So it made sense to me there that it would be they would output 5 volts.
Yeah, that's a good question. So with that, if you put 10 volts in there, we can't get higher than 10 volts without having a component in there that actually will boost it. And there are devices that actually can do that, boost devices, that will move it from a 10 to a minus 10 to a 20 to 0. And so they can shift it like that. But that's a specific component that does that. In an op amp, it doesn't do that. And so what it can only do is go as high of a voltage as you have or as low as a voltage that you have. It can't shift it. Does that make sense? Okay, so that's why it's limited to just what those rails are, and it has to be beneath that or, within that range. Does that make more sense? Okay, but good question, because yeah, it's like, well, there's a range of 20, so why can we not get 20 volts out? And that's because of the limitations of this type of internal configuration. It doesn't have that component to boost it. Okay, other questions? Yes.
Well, would it be better to think of it like, cause if you like measure the voltage the wrong way, doesn't it just give you negative voltage? So it's like, it's better to think there's just 10 going through it, like 10 to ground, just depends like which way you're thinking about it.
Yeah.
You choose the voltage.
Yeah, so it'd be 0 to 10 or 0 to minus 10, depending on which side you want to look at. Yeah. Yeah, that would be a good way to look at it. All right, any other questions? Yes.
If we have the minus 10, doesn't that mean it's a power draw? So one side of our op amp is using power and one amp is supplying power?
So it will be pushing current depending on the value out. So at plus 10, it's supplying the current out, and for a negative, it's drawing it in.
Okay.
So it will make it go in those directions. And so it's either sourcing, what's called sourcing that supply, or it's syncing it to the supply. Good question. All right, any other questions? Okay, so that is true, like if to get the positive and the negatives is changing that current direction. It's either going out from the op amp or it's drawing it into the op amp. Yes.
Could you just explain what that 3 million right there is? I'm just kind of confused about that.
So we identified, this was a comparator switch. And with that, we know this characteristic equation. And so those were just plugging in those numbers. I said just assume a large number for A naught.
Okay.
And so that was 3 minus 0 is really in there.
Okay.
And that's not possible to achieve. So that's what it's supposed to do, but it can't quite do that because it's limited by those power supplies.
Okay.
Does that make more sense?
Yeah.
Okay. All right, any other questions? Want clarification? Okay, great. Great questions. As we go through the material and questions come up, please ask and we'll readdress these concepts again after you've had time to get more comfortable with it, okay? So great that you've already had a little bit of exposure in lab, so now you're having more questions about it. So happy to address any questions as they come up. Just, it's on you to make sure you're mastering this material and these concepts. All right, so the next concept is being able to identify these op-amp configurations. So this is the next big concept. So identify different configurations. So the first thing that needs to be done is identifying, do I have a switch versus feedback configuration? So as I said, they're slightly different in their characteristics based on how they're connected externally. So a switch comparator looks like this. It has inputs in and just one output. So it doesn't have any connections, which I'll show you in a minute what feedback looks like, and then you can see the difference between the two. So if I have feedback, then I can have any of these specific types of configurations. So all of these are feedback configurations. With the feedback configurations, you're going to identify them based on input. So how many inputs? If one, I can have, no, highlight this up here, it'll be easier. See above. So with one, you can have one of these three configurations. So one input is going to be an inverting, non-inverting, or voltage follower buffer. If you have more than one, then it's going to be one of these three. So then the next step, so this would be step one. Step two is to identify which input terminal is it going to. So which input terminal are the inputs going to? So for a inverting, your input is going into the negative terminal. For non-inverting, it's going into the positive terminal. The voltage follower also goes into the positive terminal. Or into, the positive terminal, but its configuration might be slightly different. So if it's positive terminal, you could have a non-inverting or a voltage follower buffer, and then you have to differentiate between those two. For an inverting summer, it's going to go into the negative terminals, or a negative terminal. For the subtracting or difference, it's into both. One goes into the positive, one goes into the negative, and then the non-inverting is the positive input. So this is how you're going to identify what configurations you have. So actually I'm going to change these to step 3 and 4. Or I'm going to shift these. So this is step 1. Identifying is it switch or feedback. Step 2 is going to be identifying how many inputs, and step 3 is going to be identifying which input terminal are the inputs going into. Okay? Does that make sense so far? Okay. Yes.
Wait, what was the first step again? Sorry.
To differentiate, do I have feedback or a switch? So you saw the configuration for a switch, so now let's look at what feedback looks like. So so now you're going to have external configuration connected to the output to the inputs. So for feedback, your output is going to have a pathway that goes back to an input through like this. So this has feedback. So this is how you identify that it has feedback, is that pathway. So from output, so the pathway from output to the positive terminal or negative terminal. And we're only going to look at the negative. The feedback's always going to go to negative terminal here. If you have interest in kind of beyond the scope of this class, is to get into feedback systems that are not stable. There's control theory class, which is 5615. It's the classical control systems, and they talk about op-amps that actually are not stable. And so they have ones that have feedback back to the positive side and how they're used and why. So we're only going to look at what we call stable systems, which always have the feedback goes back to the negative side. So these are stable circuits. So it always will go feedback into the negative side. All right. Okay, so then identifying, is it feedback or switch? So now we're exercising the steps that I went through. And now is to look at what input terminal does, or how many input signals do I have? So here I have one input signal. And then I look at the pathway from that one to which one it goes. So following that pathway, it goes into the positive terminal. So this one is going to be a inverting amplifier. So it has the one input and it comes into the positive side. Or sorry, non-inverting. I did say inverting. Non-inverting input. So non-inverting amp is this one. So it goes into the positive and a non-inverting amp. Okay, questions about this? Okay, next one. All right, so looking again, what is my pathway? Do I have a pathway for my output? Yes, I have a pathway here to my input. And then it also goes into the input signal. So my input signal is Vs, and that pathway I follow it in, and it goes into the negative terminal. So this is the inverting amp. Is this making sense? Still looks like a foreign language. So getting comfortable with this is more and more practice of identifying these in different configurations. All right, the next one is also feedback. So I have a pathway here. It does come back and has a connection into my input. I also see that it has connections to 3 different resistors that go to voltage sources. So these would be 3 inputs. So I have input 1, V1, input 2, V2, and input 3, V3. So this is not going to be an inverting, non-inverting, or voltage follower. So it's got to be inverting, non-inverting, or subtracting difference amplifier. So to decide between those 3, I look at the pathway into the terminal and it comes into the negative input terminal. So it's an inverting summing amp. Okay, the next one. There is a pathway from the output through the R2 back into that negative terminal. So it is feedback. I then see that it has a pathway here to V1, and then I also have a V3 or V2 on this other side. So this one has 2 inputs, and there's one that goes into each side. That's what's going to be defining that it's a difference or subtracting amplifier. So you'll see both those names at times. So a difference or subtracting amplifier, yes.
So difference and subtracting is just used interchangeably?
Yep,
Okay, so
yeah, they mean the same thing. All right, so this one, my output connected back to the input. So feedback, first step is feedback. And then looking at my input sources. So in this, or input signal. So this one is here, and the pathway to that is into the plus side. So I have to say, is it inverting, non-inverting, or voltage follower? So I have 3 choices from seeing and observing that. I then have to look at what is the difference between a non-inverting amp and this one. So the difference is easier to see visually. Put this right next to it, if I can fit it. So on this, the difference is that we only have a connection on the voltage follower that goes from the output right to the negative input. On the non-inverting amp, so this is non-inverting amp. I have an additional connection on that negative side that has a connection to ground. So that is the difference. That this one has So this is the way I look at it. Again, you're gonna have to look at these and decide, like, how do I wanna define this difference? And what does it make sense to me to say what is different between these two? So this is my own words. I encourage you to come up with your own words. If that makes sense to you, great. If not, you're gonna have to be able to wrap your head around, like, okay, I look at these two and I need to identify what is the difference. This one is a voltage follower. It only has a pathway from the output back to the negative terminal. And on the negative side, I don't also have a connection to ground. If I have a connection to ground, it will not be a voltage follower. Okay? So that's the difference between those two. So this is the voltage follower. And the other word you're going to see interchangeably with it is called a buffer. So those two words will be the same. Yes?
Is the voltage follower still valid if it has a resistor R1 similar to the non-inverting amplifier?
Yep. So if I have a resistor there, it still will be a voltage follower because it doesn't have that connection on the negative terminal going also to ground. So I could have many resistors in there and they're not going to change how this operates. It does something else to it. It changes the resistance that it sees. So that's a different topic that again in 2280. He'll talk about that topic.
And so this, like, thing to recognize is the only thing that distinguishes the non-inverting voltage follower, because all the other
Yep.
steps would be the same.
Yep. Yep. So as you see here, the idea of this is like, okay, I'm starting at so the problem, like looking at this type of a problem is like, how am I going to differentiate what this circuit is? So I've tried to break it down by teaching you these steps of how I look at it. Again, you need to like rewrite these in your own words of like, is this making sense to me? If not, I need to rewrite this to what makes sense to me and be able to identify these. My thought was like I start at something and then I narrow out like what is the differences and put those into words. And then from there, I looked at, well, what is the differences? And then again, put those into words. Yes.
What did you say step 2 was again?
So step 2 is identifying how many inputs that I have going in. So in this case, remember the inputs are coming into that positive and negative side. So I have to look and see where the signal is coming in from. Is there another question? Yes.
Could you go back to the diagram, please? I was just wondering if you had a wire between the buffers loop back to the negative to the ground, would that turn it into a non-inverter?
So what do you mean if I had like a resistor here?
No, like a wire between, like, where you have that little squiggle for the red resistor you drew, if you had a wire between that and where the ground is for the buffer, would that turn it into a non-inverting?
Like here?
Yeah.
That's weird. So if I ground this, it doesn't. It won't work. I'll say that. It won't work. So it doesn't, it's neither of these configurations. So this would be like R0 for R2. And R1 over R2 will be like, it becomes a fraction when you analyze these, which we'll go into next time. But when you analyze them, it will be 1 over 0, which is not really feasible. So that's why I'm like, it won't work.
Okay.
It's gonna not be happy with you. Okay, other questions though? But a good thought, like yes, that would be kind of the concept, like yes, there's a pathway, so then is it the non-inverting, but it won't work like a non-inverting. So it will not be happy with you if you did that and may even blow your op amp, so don't connect it without a resistor there. So you do want to stick to one of these configurations to make it work as you expect, like that configuration. If you come up with, if you have something else, a lot of times you're going to create like a Thevenin circuit, and then that would then be one voltage and a resistor. So if you have a kind of a complicated circuitry like connected to it, you're going to reduce that down to a voltage and a resistor from a Thevenin, and then see like, does it match any of these configurations? Okay, other questions? Yes?
Can I see the difference subtracted?
All right, any other comments, questions? Okay. All right, then the last one is a non-inverting summer. So again, we have to start at the step one, which is there a pathway from that output back to this input? And I identify like, yes, there's a pathway there. Then I want to look at the inputs, and on that positive terminal and negative terminal, I see that there is a source here and a source here, which can act as inputs. And they're both going into that positive terminal. So that's where the non-inverting summing comes in. Okay, so these are all the examples of how to identify these. Now it's up to you guys to practice a lot. So we're going to do one more grouping of configurations. You guys get to practice these skills, and then it's on you guys to master this as far as doing as much as you need to with all the practice problems till you're comfortable with it. Okay, so I was able to get Unit 3, pretty sure I got Unit 3 up. Practice problems. If not, I'll have them up by tonight so you can get more practice. And then next week's homework will be on identifying the op-amp configurations. And then our next period, we're going to go into now, like after we've identified them, the next step is analyzing what is my actual output is for that configuration with specific values in there. So we'll go through the analyzing them of getting an output value next time. So okay, so what is this circuit?
Switch.
Thank you. I heard people saying it. So switch comparator, correct? So there's our switch comparator. Okay, so we looked at it, no feedback, so there's no pathway from that output back to the negative terminal. So it's a switch, feedback, and we're done. So this one's the easiest one to look at and be like, oh, that's just a comparator. And then you're done. Okay. What about this one? Okay. So positive side, yes, feedback, and a non-inverting amp. Good job. What about this one? Good. Inverting summer. So it does have feedback. I have 3 inputs, and they go into the negative terminal.
Is it always going to be 3 inputs?
No, it can be more than one. So it could be 2, 3, 4, 5, 6, and I can keep adding on as many as I want to add these up. All right. What about this one? Good. Subtracting difference. So I see that there are 2 inputs, and one is negative and one is positive. All right, this one. Had a little cheat on there. Yes, non-inverting summer, good. So I see that yes, feedback, 2 input signals goes into the plus, so non-inverting summer. All right, this one. Correct. So identifying that it is feedback, And then my input VS goes into the negative side, so inverting amp. And one more. And this one. So buffer or voltage follower. And again there, and plus, and no connection on that negative side to ground. All right, so again, practice until you're comfortable with these concepts. We're going to move on to the next concept, next lecture. You will need to do the Unit 2 feedback for Thursday. It will be due tomorrow, and then next week will be your next homework on this with the quiz. All right, have a good day. What? No homework or quiz this week, so it will be just the Unit 2 feedback.
I was wondering how the zero currents is